I decided to end the other part of this lecture to start a new one so that it's not too long in a single sitting. Now, let me give you some properties of the definite integral. And again, when you get to calculus 2, that's when you really are going to see all of these things come to fruition, because the whole class will be spent on finding ways of solving definite integrals. So these are two special integrals. Number one, if f is defined at x equals a, and we define the definite integral from a to a of f of x dx, and this is equal to 0. And this is, this is something that you could clearly see because it has no height. It's just a one-dimensional image. It's like if you have something like this and you're talking about the axis itself, there's no area underneath it between the axis and the axis. Okay? Well, in fact, I'm really talking about the height. For 2, the second important definition is that if f is integrable on the closed interval a, b, and this is important, this one we use a lot, we define the integral from minus a to b, from b to a of f of x dx to equal to negative a to b f of x dx. Basically, what this means, what number 2 means, is that if a is bigger than b, then we can rewrite the integral. So the integral is always written from the lower bound to the upper bound. And naturally, a is less than b. Remember, b is the upper bound, a is the lower bound. But when we reverse this, we have upper to lower, then you need to rewrite it as negative lower to upper bound. So that's what's happening here. We rewrite the limits of integration from lower to upper bound, and we introduce this negative sign in front of the integral. Okay? So just a quick example of these two things. If somebody comes up to you and gives you the integral from pi to pi of sine of x dx, then you know that it's equal to 0 because we're going from a equals pi to b equals pi. So by definition, that is going to be equal to 0. And similarly, what if somebody told us, okay, find the integral from 0 to 3 of x plus 2 dx. Notice that 3 is less than 0. Okay? So we have the lower, wrote this wrong. 3 is bigger than 0. That's what I meant to say. 3 is bigger than 0. 0 is less than 3. But we have it written as the lower bound being 3 and the upper bound being 0, which is not right. Now this example is the one that we did earlier in the first part of this video, which is the trapezoid, which has 0 to 3. And we know that that is equal to 21 over 2. So by our second rule now, we could rewrite this as negative 0 to 3 of x plus 2 dx, and we know that this part is equal to 21 over 2. So we have negative 21 over 2 because this piece is positive, but we have a negative in front, so we get negative 21 over 2. Okay, so that's two very important rules of integration. Another important rule of integration is the following. If f is integrable on the three, this one is also used a lot, three closed intervals determined by A, B, and C, then the following is true. If you have an interval, let's say from A to B, for f of x dx, or the function of x dx, then you could actually go from A to some middle number C. So C is in the interval A to B. Okay, C is some number in between A and B. So you could go from A to C and then add the integral from C to B. So you could split the integral into two pieces. So for example, say your function looks like something like this. Right, this is f of x and y. Let's say this is A, this is B. And we were looking at this area right here, right? And what this is saying is that if you pick some value C in the middle, then you could look first at this piece, which has length AC, and this interval AC and this interval CB. So you can look at this integral and then add it to this integral. You'll get the area of both of these rectangles. This is not really a rectangle, it's a curve. But you get the area of these two figures, and when you add them up, you get the area of the entire interval, the entire closed interval. So it's something that you actually do use a lot. Let me do actually a quick example of that. Let's say you have the integral from -1 to 1 of the absolute value of x dx. By definition, you should know from pre-calc what the definition of the absolute value is. From -1 to 0, the absolute value of x is equal to negative x. And so basically, when you have the absolute value of x, when x is less than 0, you have negative x, and when x is bigger than 0, you have x. And obviously when x is equal to 0, then you get 0. In any case, so that's where I'm getting this minus x from this top piece, dx, plus 0 to 1 dx, x dx. So what I'm doing is, instead of going from -1 to 1, I'm going from -1 to a middle value, which is in this case 0, and then I'm splitting the integral into two pieces. Now, the function for y equals absolute value of x looks like this, right? It looks like a v. And at 1, you get 1, and at -1, you get 1. Now, what area we're looking for? We're looking for both of these areas. We're looking for this area, we're looking for this area. And notice that they represent triangles, and we know how to find the area of a triangle. The area of a triangle is 1/2 base times height. So what is the base here? The base for both of them is 1. The height for both of them is 1. So what we have here really is 1/2 plus 1/2, because if the base and height is 1, then for both of them you get 1/2 times 1 times 1, which is 1/2 plus 1/2, which is 1. So the area of these two sides is just 1, and that makes sense. That makes sense. Okay. So notice here that we split up the integral into two subintervals. Let me give you another property of integration. So this is the last one, well, the second to last one that I'll give you. I'll give you one more. If f and g are integrable on the closed interval ab, and k is a constant, and this too shouldn't surprise you, then the function k times f and f plus or minus g are integrable on the closed interval AB. And the following is true. Okay, so the following is true. So 1, the integral from a to b of k times f of x dx is equal to k times the integral from a to b of f of x dx. So again, constant multiple rule applies. And 2, the definite integral from a to b of f of x plus or minus g of x is dx is equal to the definite integral of from a to b of f of x dx plus or minus the definite integral from a to b of g of x dx. So if you have the sum of two functions, you could separate the integral. And this applies for more than just two functions. It applies for, if you have 5, 6, or even 10 functions. Let's do an example of that. So let's say somebody asks you to evaluate the following function, the following definite integral. Is the definite integral from 1 to 3 of minus x squared plus 4x minus 3 dx using the given information. And the given information is the following. So this person that gave you this problem for you to solve because they didn't like you very much told you that the definite integral from 1 to 3 of x squared dx is equal to 26 over 3. They told you that the definite integral from 1 to 3 of x dx is equal to 4. And they came in and told you that the definite integral from 1 to 3 of 1 dx is equal to 2. Remember, if I don't write a number here, it's just a 1 there. Well, the problem that we have is the integral of 1 to 3 of negative x squared plus 4x minus 3 dx. Now, using the two rules that I gave us, we can solve this. First, we can separate each of the terms by using rule number 2. So we have the integral of from 1 to 3 of negative x squared dx plus the integral from 1 to 3 of 4x dx plus the integral from 1 to 3 of minus 3 dx. Now, by the constant multiple rule, we can pull out certain things. So from the first one, I could pull out a negative 1. So we get x squared dx. From the second one, I pull out a 4. So I get x dx. And from the last one, I'll pull out the whole negative 3. So we get 1 over 3 dx. And notice that now I can use the given information. Why? Because I know that this is equal to 26 over 3. I know that this is equal to 4. And I know that this is equal to 2. So again, this piece is equal to 26 over 3. This piece is equal to 4. And this piece is equal to 2. So what do I have left? Well, I have negative, because the negative side is in the front, 26 over 3 plus 4 times 4 minus 3 times 2. Okay, so I'm just multiplying the constant in front of the integral by what the integral is equal to. So I get negative 26 over 3 plus 16 minus 6, which is equal to negative 26 over 3 plus 10. And if you multiply 10 times 3 and divide by 3, you get negative 26 over 3 plus 30 over 3, which is equal to 4 over 3. Okay, so we now have a way of actually solving the sum or difference of integrals. Okay. Now, the last thing that I will say for this section is the following. This is called the preservation of inequalities. It is not often covered by instructors, but given that we're online, I have time to cover this. So if f is continuous, this is not on your final, by the way, this piece. So the stuff on your final ends here. So if f is integrable and non-negative, on the closed interval AB, then the definite integral from a to b of f of x dx is bigger than or equal to 0. Okay, so if you're non-negative and you're integrable on a closed interval AB, then you're at least, the least that you could be is 0, because you're not negative. If f and g are both integrable on the closed interval AB, and f of x is less than or equal to g of x for every x on the interval AB, then, as you probably will suspect, the definite integral from a to b of f of x dx is less than or equal to the definite integral from a to b of g of x dx. So this inequality is preserved. Okay, so that's the last thing that I'll mention in this section about the definite integral. On the next lecture, we're going to talk about the fundamental theorem of calculus, which will give us a sure way of actually evaluating these integrals. We'll talk about the extreme value theorem for integration, and if we have time, we will talk about the so-called second fundamental theorem of calculus. Thank you for your attention.